The one thing I'll say about Jay is he is distinguished both as a field hydrologist. You know, all my students read his papers on soil moisture monitoring, and the work that he's going to talk about today, using GRACE to do soil, to tell us things about how much water we have and where it is. But as a hydrologic modeler, Jay is also someone that I turn to. He is within QUASI, which is the big US consortium of hydrologists. He's running CHIMP, which is our community hydrology model. So he could have given a talk on modeling. We had to choose between which of the distinguished fields he was going to talk about. He chose to talk about GRACE, but you could also ask him about modeling at the end. So with that, I will turn it over.
Thank you very much, Christina, for that distinguished introduction. And the reason we know that I'm distinguished, and I need to write it here, it's actually called the Berthold Dreiss Distinguished Lectureship. So that I never knew before, and now I know. Yes, I am on tour, and I'm at the beginning of the tour, and it's like roughly one a week, and I'm all retired. And this is number 4, but actually it's the first one of 2012, and I did 3 kind of warm-ups before Christmas. It's been fun, and it's a great opportunity to come out and visit programs like yours and meet with students and tell you a little bit about the work that I've been doing with the GRACE mission. I've spoken about it here before, but as I think back about the last time I was here, it was very early on in the mission and maybe hadn't even launched yet. So, you know, it's probably last year, 2002, 2003. So it's a nice chance to update what's been going on. So I need to acknowledge the Geological Society of America. So the Berthold Dreiss Lectureship is actually in the hydrogeology program, and it's been awarded every year for about 30 years now. And I encourage you to take a look at the GSA webpage and see some of the people that have done it before, and you'll recognize them from the names on your textbooks on your shelf. So it's really been a great lectureship. And also support of the Office of Research and the School of Physical Sciences at UCI. And of course you guys, thanks so much for having me out. Here's my map as it looks right now. These are not ones that I've done, they're just ones that are scheduled. And I'm really only scheduled through the winter quarter. So I've gotten about 100 invitations for about 50 slots. I'm really looking forward to going here. This is Hawaii. This is the Chapman Conference. And looking forward to, of course, happy to be here, but looking forward to adding more little push pins all over the place. One of the things that I've been doing to maintain sanity while doing this is to actually write a blog. And so I encourage you to take a look at it. And after every lecture, I write up a little lecture sort of report on what I saw. And so I've already taken pictures from your awesome balcony and other ocean views that will be in there. The address is blog.ucchm.org. And I'm actually using it to write some opinion pieces based on some of the talks that I've done. So I've got one on there that's posted right now about basically, it's the text of this lecture that I'll give, so it's a nice reference point, and I'll leave the slides with Christina as well. Okay, so here's what I'll talk about. I'll talk about water cycle change and water cycle acceleration. It's a term that we hear a lot, and so I'll give you my perspective on what I think it is and what we're seeing. And a lot of that, most of what I'll show you comes from the GRACE mission. Not all of it, but much of it. And actually, a lot of it's not published yet. Hopefully, will come out sometime this year. And so to do that, I'll sort of put it in this context of, if the water cycle is actually changing, what might we expect to see versus what we actually are seeing? So think about what we might see and then go and look and figure out if we're actually seeing it. Then I think we need to be thinking about how the water cycle is going to behave in the future, because we hear a lot about water cycle acceleration. And so I think we need to start thinking out in the future, especially in the context of some of the things that I'll be talking about. What's it going to look like 50 years from now, 100 years from now? No reason not to think about 200 years or 300 years. So it's quite speculative, but I think that we should start thinking about it. And then what should we be doing about it as students and faculty? And you're here, and so you're in the program here, so you're already off to a great start. Okay, so let's talk about the GRACE mission and the characterization of water cycle change, what I mean in the context of this lecture, and then a little bit about GRACE. So one of my standard lines that I've been saying for a long time is that one of maybe the most palpable impact of global change may ultimately be changes to the water cycle. Okay? And of course that's going to affect freshwater availability. So a lot of what we think about when we think about climate has to do with water, humidity, rainfall. Okay? These are first order things. So in a warming climate, these are some things that we can expect. And so models predict, and I think observations are beginning to suggest that some of this is actually happening. So in a warming climate, we can expect more evaporation, okay, because the atmosphere can hold more moisture as it warms. And if we have more evaporation, then what goes up must come down, so we'll have more precipitation. Well, that probably means more runoff. Okay, so these are things that we should be looking for. We should be looking for bigger exchanges or more cycling of water in the water cycle. So are we seeing that? Another thing that gets discussed a lot is the changes in the extremes. Okay, so we should probably be expecting an increase in the magnitude of and frequency of the extremes. Okay? Now, yes, we'll probably have more rainfall, but it doesn't mean that it's going to fall uniformly. So almost by definition, there'll be some places that are going to have more rain, some places that are going to have less rain. And the energetics of the situation, of the latent heat, of vaporization and condensation suggests that there'll be more energy exchange, which translates into more energetic, more extreme events. The third thing that gets talked about a lot is the redistribution of precipitation from the mid-latitudes to the high latitudes and the low latitudes. So the wet areas get wetter while the dry areas get drier. And so this is important because in a lot of those dry areas, we rely on groundwater because they're dry and there's not much surface water. And so I'll return to that point because there are implications for the rate at which we're using available groundwater in the dry, arid and semi-arid parts of the world. So collectively, in the context of this talk, I call these three things the bigger fluxes, the bigger exchanges, the more extreme extremes, and the wet areas getting drier, wet areas getting wetter, dry areas getting drier. Those are the three things that I think of when I, in this talk, we'll be talking about water cycle acceleration. Okay, so GRACE stands for Gravity Recovery and Climate Experiment. A lot of you guys know about it. It's been around for almost a decade now. Let me just briefly explain how it works. It's a gravity mission. Okay? It maps Earth's gravity field and changes in the gravity field. The mission looks something like we show here on the right side. These are the two GRACE satellites. They are about the size of I don't know, a minivan or something. So they're not very big. They are about 450 kilometers at altitude, and they're separated by about 220 kilometers. Okay? And so these guys are in a near polar orbit. They orbit around the Earth, and they are, what's different about the GRACE mission is that the satellites themselves, they're not looking at the ground. So it's not any kind of an optical mission. They're not taking pictures of the ground. They're sensing mass differences. Okay? So what happens is as the first satellite orbits past a mountain range, it gets pulled down, right? So that mountain range is heavier, so it has a greater force of gravitational attraction, and so the first satellite in the front of the line gets pulled down and accelerated towards the mountain range, and then drifts back into its orbit. Okay? And so that distance between the two satellites changes. Okay? Then the second one comes in, it gets pulled down. Right? So you have the distance between the two satellites constantly changing. And so basically mapping mass variability over the Earth. Okay? And it takes about a month to make a gravity map. If you do it repeatedly, then you can map mass changes in the Earth. So say we're orbiting over the Sierras this month, and we get a certain distance, and we translate that into gravitational attraction and make a gravity map. Well, then it snows. We come by next month. It's heavier. Okay? So there'll be a difference in the gravity field, and that difference in the gravity field, excuse me, is primarily related to, is like 99.9% related to the change in water. The reason that it's related to the change in water is that on those time scales, that's the dominant thing that's changing. Okay? There are the occasional huge earthquake, which we can correct for, okay, but things like plate tectonics and mantle convection, those things are too slow to affect the, the gravity field on these monthly timescales. Post-glacial rebound, it highlighted like Greenland and Antarctica is something that we do correct for. So the main thing that we're seeing is changes in water storage. Okay, so we've got these precise measurements of the position between the satellites and the changes in the distance that we use to produce these very accurate gravity maps at monthly and longer time scales. I make it sound like the two satellites are on this giant spring and they're really moving apart quite a bit, but the distance that they're actually moving, the perturbation, is at the micron level. So it's 1,000th of a millimeter. And the accuracy with which that difference is measured is a 10th of a micron. Okay, so it's kind of mind-boggling, actually, when you think about it. This mission was supposed to only last, it was a ES, Earth System Science Pathfinder mission, excuse me. So it was supposed to last for 5 years. And it's been going for almost a decade now. Now it is losing some battery life. And so we're down to getting measurements 10 out of 12 months out of the year. Follow-on is planned for 2016. A carbon copy of the mission that's flying right now. I like to say GRACE is like a giant scale in the sky. Okay? It doesn't tell you how much you weigh. It doesn't say, it's time for a diet or anything, but it tells you how much you've gained or lost in a particular month. So, considering that we've never had those kind of observations before in hydrology for big river basins, for continents, it's great. It's great new information. So I just want to see if I do have the space-time constraints I'll get to in just a second. So then conceptually, here's sort of what GRACE is doing. Before GRACE, this is what the gravity field looked like. Thank you very much. So before GRACE, the gravity field looked like this, our knowledge of the gravity field. And then after about 100 days of GRACE data, you can see those features really sharpening up. And then after a year, they're much, much sharper. And then today, we've got a great map. And so really, in a sense, what we're doing is mapping this every month and then looking at the difference. And that difference is driven by changes in water storage. Okay, so I've kind of said this. The difference between the two maps is the time variable part. The main contributors to time variations are water storage change in the ocean, atmosphere, and on land, because water is extremely heavy. So really what we're seeing is the change in water storage. I should point out that what we're really seeing is the change in all the water stored in a river basin. So if this is a river basin like the Sacramento, San Joaquin river basins, we're seeing the change in all of the water storage. So all of the snow, all of the surface water, all of the soil, moisture, groundwater, okay? And so the only way we can split it apart is with other data sets. And hopefully those will add up and close the water budget. And so we've done a lot of that work, and I'll show you some of that. So yes, the space-time sort of resolution, we really use it at scales of 150,000 to 200,000 square kilometers and greater. So it's a large area. Okay? It's not a hydrometeorological mission. It's more hydroclimatology. And it's monthly and longer. There are some data sets that are 10 days that are pretty good, but they're quite computationally intensive to put together. So here's what some of the data look like. This is for the Sacramento, San Joaquin, and so these are monthly, basically anomalies in water storage. They're in millimeters, so anomalies with respect to the average of the time period, which here is 2003 through 2010. So you see, each dot is a monthly storage value. So we see the ups and downs, which we've never been able to see before. We can see trends. This was during the drought. There was a lot of groundwater depletion. There wasn't as much snow. And almost every time I touch base with Jeff, he says, oh, yeah, that makes sense because this year there's this much snow, and this year there's this much snow, and this year there's this much snow. And so that's exactly the kind of stuff that we need to keep on doing as a reality check. Speaking of reality checks, I've got so much information here, so much results-oriented stuff. We went through a very, very long phase, years of validation work. And so I recognize that it's not in the talk, but we've written so many papers where we've compared GRACE observations to just about everything that we can get our hands on. And there's not much ground-based stuff, but we compare to models, we compare to land, atmosphere, water balances, we compare to whatever available observational data sets we can get our hands on. And most of the time it looks really good. Certainly gives us enough confidence to talk about the things that I'm talking about today. And if anyone is interested, I can give you references, show you where all that validation work is. So if you go to the NASA JPL website, you can find an animation and all the data sets. And it looks like this. And so in this animation, red, and I unfortunately will flip the scale around on you a couple of times in this talk. I tend to use red is drier and blue is wetter. And JPL does the opposite. But in this animation, so red is wetter than average and blue is drier than average. And so these are monthly changes. And so you can see, it's fairly blobby stuff. That's a technical term. So it is what it is. It's not going to help us predict the weather in Santa Barbara tomorrow, but it will definitely give us a good feeling for how storage has changed in the Central Valley and the Sierras, over the last season. Okay, so that's one way we look at the data. I showed you time series for the Sacramento San Joaquin. Another thing we do is look at these maps. Okay, and these maps are quite interesting. These are these are through 2009, I think. Actually, the signals that I'm showing here, the amplitude of the time series. So the amplitude of the ups and downs in the XY plot that I showed you is shown here, where red is greater and blue is smaller, and the trend. Okay, these are actually fairly stable now that we have several years of data. So if I put up the 2000 and the data that go through 2011, it basically look just like they look the same. So what this is showing us here, what we've come to recognize is that the amplitude really shows us the strength of the water cycle, and I'll get back to that. Okay, so it's a measure of the strength. It's a measure of also a measure of the variability. And these trends are important because they show us human behavior that we kind of knew was happening, but didn't really have a global picture of before. So for example, there's a lot of, here blue is losing water. So we've got areas where, these blue bullets, this is actually a Sumatra earthquake. But obviously the ice sheets are losing a lot and the glaciers in Alaska and Patagonia. But a lot of these other blue regions here are related to groundwater depletion. Okay, and I'll show you a better map in a few slides. But this is important because I hope I will make the case that this is the kind of stuff that we need to get into our models. Okay, we need to, one of the problems that we have with models is capturing variability. And so now we have a measure of the strength of the water cycle, the ups and the downs. How much does storage go up? How much it goes down? How much does it go down? Well, that's an integrated reflection of how much precipitation, how much evaporation there is. So, all of our data sets and models need to be consistent. So I would argue that we need to capture some of this, and our models, especially global models, do not do a good job with human water management. We don't have in our global models groundwater extraction for water supply, yet some of these signals are extremely strong. And enough people have done other related work that shows that the interactions between the land and the atmosphere are coupled through this wetness. So I would argue for better climate and weather prediction, longer term seasonal weather prediction, not short term, and of course for better prediction of water availability. This kind of stuff we need to get into our models. So we can take these data, we can plot them, we can do all kinds of different things. And so these are just time series for different major river basins. And again, I show these because it's the kind of information that we've never had before. So I've got trend lines in here, but some of the places the trends are pretty obvious, and we know what's going on. It's been happening for a long time. In a sense, the more important thing that we need to recognize is that we now have a measure of the storage variations. We can see the ups and downs. Okay? And over the long period, we'll be able to separate out what's an interannual variation and what's a long-term trend, and maybe if it's due to climate change or human water management or something else. But I think it's pretty clear that it's kind of nice to have this information. So I'll talk about how we've used it in some of our research next. So I want to, in this part of the talk about these three aspects of water cycle change. So the increasing fluxes, okay, is the evaporation getting bigger? Is the precipitation getting bigger? Is the runoff getting bigger? The changes in the extremes, and the redistribution of precipitation. All right, so this is a slide from a NASA project that I'm involved in. And it looks like a global water cycle figure that would be in one of your textbooks. And the numbers are actually pretty close. But the difference is that we derived all of the numbers from satellite data sets. So there's some differences that are important. But it's your standard water cycle figure. And so we've got evaporation greater than precipitation over the ocean. And so there's a vapor transport that feeds precipitation on land. And then we've got a return flow. One of the things we sort of hypothesized or decided we wanted to take a look at, in part because of the availability of some decent data sets, was, hey, okay, if the water cycle is accelerating, well, the ocean's pretty big, and so maybe we're going to see an increase in precipitation over the ocean. Maybe we're going to see an increase in evaporation. And what we were thinking was maybe that difference, the P minus E or E minus P, will increase the vapor transport. Basically, we're trying to look at, is discharge going to increase? And so what we did was do a water balance on the ocean, okay, by using these. We used GRACE data for mass change. We used some temperature data to figure out what the thermal expansion component of sea level rise is. We used altimetry data to look at sea level rise. So we figured out what the mass change component of the ocean was. And we had these products that are part of this NASA Energy and Water Cycle Studies program for evaporation and for precipitation. And from that, we solved for stream flow. Okay? So just to show you sort of in a picture form, here's a box diagram of the global water cycle. And so we're expecting that if these guys get bigger, then this will get bigger, especially if the difference between them gets bigger. That would lead to an increase here and increasing discharge. So basically, what I'm trying to say is increasing global discharge may be an indicator of water cycle acceleration. Okay? And so we went and took a look at that. And so we looked at this period from 1994 to 2006. And here's what we found. We found that ocean precipitation increased by about 240 cubic kilometers per year. And this is the red dashed lines are the trends for the whole time period, and the blue solid lines are the piecewise trends. We found that oceanic evaporation actually increased a lot in this time period by 768 cubic kilometers per year. And these are accelerations, right, when you look at the units. And so the discharge was changing by about 540 cubic kilometers per year. And so it turns out on a percent basis that it actually seems like a small number. It's like just over 1%. It's 1.5%. And this is just the time series of the discharge on a monthly basis and then annual. So you can see there's a slight upward trend. You can see it a little bit better here, albeit with the big intraannual variations. Okay? But so there's a message here that is we can track global discharge in a way that we could never do it before. We see a little bit of an increase, and that increase, although it's small, it's significant. It's statistically significant, and actually 1.5% per year. Let's just say that we probably don't want stream flow to be increasing more than that because your campus would be underwater pretty soon. So, so this is sort of one study that we've done that we think sort of underscores that the water cycle may already be accelerating. If those trends continue, it may be what we, could be a smoking gun. And of course, there's all these implications for land contributions to sea level rise, increased flooding, changing flood risk, and inundation mapping. So these are all things that we need to be paying attention to in the future. Okay, so the second thing, part of the water cycle acceleration is the increasing variability. And the way that we've approached it is by, if you think about those time series that I showed you of the GRACE data of storage, they go up and down, right? And so we're, when you think about what leads to those ups and downs, a picture of how we can quantify variability change emerges. So imagine we're looking at storage in the ocean, and then we're going to get a GRACE time series of mass change in the ocean. We could do the same thing for land. We've done it. So if we're going to, so again, just think about our inputs and outputs, evaporation, precipitation, and river discharge, including the ice sheets, into the ocean. So they'll lead to a time series that looks like this, right? So these are actual GRACE data for ocean mass, global ocean mass variations, monthly data. And so it's storage versus time. And so the inflows, the precipitation and the discharges inflow into the ocean will lead to an increase in storage, and outflows like evaporation will lead to a decrease in storage. And so if we think about then a changing water cycle, maybe the ups and downs are going to get bigger. If the precipitation and the discharge increase, then it's going to go up more. And if the evaporation increases, it's going to go down more. So these storage time series become an integrated measure of the ups and downs or the variability in the water cycle. So the amplitude is really a measure of the water cycle strength. Okay, and so again, with the GRACE data, we've never really had that sort of integrated measure before. So it's not rocket science, but we've never had it before, so it kind of took us a while to figure out what we had right in front of us. And then by extension, then changes in these changes in the amplitude are a measure of the change in the strength of the water cycle, or a measure of water cycle acceleration. Okay, so that's what we were thinking. So this in part grew out of this plot here that we've been updating and working on for a long time. I still haven't published it yet. This is a plot of all of the water in the world. Okay, so all of the water in the ocean, all of the water on land, all of the water in the ice sheets. The atmosphere is not on here because it's very small compared to the storage in the land and the ocean and the ice sheets. Really what it's showing is the mass change of the oceans on a monthly basis, so going up and down. The units are, this is all normalized to how much sea level will go up and down. So it's units of equivalent mean sea level height in centimeters. And so the out of phase with that is the land storage. So one goes up, the other goes down, right? And that makes complete sense, right? Because that's the water cycle. Okay, that's the precipitation on land and runoff back into the ocean. Okay, that's the water cycle, and so that's kind of cool. We see that those variations are way bigger than the variations of the ice sheets, but the ice sheets have a pretty steady downward trend because of the melting. So one of the things that got us thinking then about the strength of the water cycle and the variability stuff were these ups and downs. And up until about this point in time, I would look at this and see, wow, that amplitude is really increasing quite a bit. And I think that means something, and I think it means something about the strength of the water cycle. So we fit different cone functions, and it looked great. And then we got over here, and it looked like it was going down. And so our idea of having this paper that had like expanding cones that showed increasing variability died because we didn't publish it quickly enough. But what we decided to do instead was just make a plot of the amplitude. And so we decided that if we plotted the amplitude, if you're plotting the amplitude, you're plotting the strength of the water cycle. Okay, and so this is how it's changed over the GRACE time period. The blue is the ocean, and the green is the land. So this is basically saying precipitation is increasing by a certain amount, and evaporation is increasing by a certain amount, and the balance sort of gives you an increasing strength that looks like this. It's the ups and downs, right? The ups and downs are getting bigger. So the variability is increasing. And if we put a trend line through here, then that would be an acceleration. So those would be acceleration units. So again, this is work in progress. Of course, I think it's really cool because I work on it. But you guys can ultimately be the judge. We think it's kind of interesting. I threw this in here because I gave a talk at Texas, and I just wanted to take a moment to say that I think that a lot of the GRACE data, so we're talking about variability, and so Texas had a huge drought, right? And we're always having floods in the U.S., in particular in the Midwest and the Mississippi. And so when I went to Texas, I pulled out some of the data for the Rio Grande and the Brazos and the Arkansas Red River. I thought that there was more information there than is being utilized. And so just the next two slides basically are that pitch that there's more information in the GRACE data than I think we're able to take advantage of for a number of reasons, one of which is funding and lack of human resources. But when you look at the Rio Grande, and when you look at the Brazos, let's look at the Brazos. I mean, that's a very strong decline signal. And every year the low just gets lower and lower. But when people talk about the drought in Texas, they're only talking about the last year. Okay? I look at this and I say, I mean, we don't have a crystal ball or anything, but you can kind of see it coming. You can see these low parts. The low spots getting lower and lower every year. And this is actually the combination of the basin. So this is like all of the water in Texas. Okay? And so, you can kind of see that there's a steady decrease. So all I'm saying is, it would be nice to be able to do this sort of information transfer with some of our state and federal water planning agencies better than we're doing it now. Likewise, we can look at the flooding side, and these are from a couple of years ago, looking at the Mississippi. So Mississippi, and then the upper Mississippi Basin, and then the Missouri. And so we had a flood sometime in here. I mean, when you look at this, to me this says there's trouble coming, all right? And we're not using it in any formal way, and I think that we should. So basically, this is a pitch to the students out there to think about how you can use it in your research. It's a very small group of people that works on GRACE data. There's a lot of information there. This is just one example of something that hasn't really been done. Okay, so there are implications for this increasing variability, and they're quite important. And the reason they're important is because if we have more evaporation, that means more energy, right? More energy is required, and more energy is being transferred, and more energy is going to be released when that water vapor condenses into precipitation, right? So the more you have going up, and the more you have going down, and the more you have transported around, there is a coincident acceleration in the energy cycle that has huge implications for storms and for droughts, okay? So that's why I think that's important. And then, with respect to water management, the whole idea behind water management is to smooth out that variability, to provide reliable water supply, right? And so the more variability we have going into our water management system, the more challenging the task of providing that reliable water supply becomes. There's also, we don't talk much about this in pure sciences, but I mean, there are huge socioeconomic, political, security, and other risks that are associated with that increasing variability. Okay, there are whole lifestyles that are based on a certain amount of variability, and as that changes, it throws the socioeconomics really off kilter, especially in the developing world. So yeah, I mean, the one thing that society wants and economic growth requires is a sustainable, reliable water source. And so I'll show you a slide towards the end that says maybe this is going to become more of a challenge in the future. The third part of the water cycle acceleration is this redistribution of precipitation from the mid-latitudes to the high and low latitudes. This is an IPCC figure that looks at that for a certain scenario for the winter, for the summer, at the end of the 21st century. Okay, so the red is decreasing, drying out, and the blue is increasing precipitation. So models are showing this, and so I've looked at my GRACE data enough to believe that I actually see some of this going on there. And so now I've changed the scale, and for the, not for the last time. Red is decreasing, blue is increasing. So red is drying out. So all these red spots are, a lot of this is groundwater depletion. But you see a lot of that yellow and red, it's like in the mid latitudes, and a lot of this blue is across the tropics, and there's a lot of blue up here. So when I put my blue and my yellow goggles on, which I'm about to help you with right now, whoops, this is what I see. Here's the yellow goggles. These boxes actually have a faint yellow tint, okay, just to help you lead your eye. But I think there's a lot of drying in the mid-latitudes, okay, and that's a little bit more obvious blue goggles. But yeah, there's more blue at the high latitudes and in the tropics. And so, I asked the question: is this redistribution already happening? Okay. The other thing that's kind of scary is when you actually look at all these blobs. I've labeled just about all of them where we've looked. Okay. And so a lot of what we see again. So these are just labeling the trends, what's going on in the world. And so this is the part that I sort of call the human fingerprint, on global water storage. So we've got the biggest signals, the ice sheets, Greenland and Antarctica. Probably the next biggest signals, the glaciers in Patagonia, Alaska, a little bit around the Tibetan Plateau. The other huge ones, the red ones, are mostly groundwater depletion. Okay, India, Tien Shan region, Middle Eastern, terrible, North China Plateau, Mongolia. This is a little bit of a drought signal. I'll get back to that. High Plains, Central Valley. A little bit of drought signal going on here in the Amazon. Big groundwater depletion here. Big groundwater depletion here, mostly associated with mining. Okay. One of the challenges of doing this work is it's really tough to do the attribution because when there's a drought, we use more groundwater. Okay. So it's difficult to pull it apart in some cases. So some of those signals are mixed drought, groundwater. That's just what we do. Right? And so we would just need a lot more data to be able to pull it out and say, oh, this is from lack of rainfall and recharge. This is from human water use. So one of the shortcomings of the GRACE data is that you need a lot more, but on the positive side, I think it's pretty compelling. I just want to show a few slides. I should probably start to wrap it up. Show a few slides. We've written a lot of papers on groundwater depletion, and I just want to show you how we do that. And it does involve additional data. Because GRACE gives you the change in all of this, right? And if you want to study groundwater depletion using GRACE data, and it's a good tool for that because it weighs the total change, and a lot of the change can come from groundwater. Well, then you have to get data on the snow and the surface water and the soil moisture, right? So you have to strip off this upper part above the stuff, the snow and the surface water and the soil moisture from the GRACE signal to isolate the groundwater. Okay, so that's what I'm showing here. And so we've done that. It's become kind of like a stupid pet trick for us. We just keep doing it over and over again. So let me show you the California stuff, because here we are in California, and the Central Valley is super important to the state's economy, to food production in the United States. So I don't have to elaborate on that. To this audience, maybe the students know, maybe don't, maybe they don't. You know, I actually didn't. That 20% of our demand for groundwater in the U.S. is in the Central Valley. It's the second most pumped aquifer in the United States behind the Ogallala. So these are things I didn't know. And of course we know, you know, there's been subsidence there and depletion and subsidence for years. This famous picture of the well casing, and so the land surface has dropped that much because the groundwater's been removed. So the fact that there's depletion there is no secret. But what GRACE allows us to do in combining some of these macro scale data sets allows us to quantify it in ways that are otherwise quite difficult. You know, it's very difficult you have to do a big groundwater modeling study, compile hundreds and hundreds of well data, and you know, we start trying to do that, say, internationally, you can't do it, right? You can do it in the US, and the USGS has done a great job, and our data are consistent with, and our results are consistent with theirs. But when you start looking around the world, you can't do it for all the reasons that we encounter. You know, the lack of data transparency. Lots of countries don't want to share their data because for defense reasons, for socioeconomic reasons. Yep.
Substance makes no difference to GRACE.
No, right. It doesn't. It's just mass change. Right. Yeah. Right. One of the things that we're actually trying to combine with GRACE is GPS and INSAR. We're doing a little bit better with the GPS, and nothing to report on the INSAR. Okay, so just from a purely mass basis then, we've got our GRACE signal, and we can subtract from it snow water equivalent, which one of these days we're going to get from Jeff, but at the time we did this, we used NORSC data that we got from Don Klein, surface water from the database, from the state databases, and soil moisture we have to take from a model. We just took it from a regional land surface model because we don't really measure it. So if you subtract this and this and this from this, you're left with this, which is the groundwater signal. The red lines are the piecewise trends. The blue line is the trend for the whole time period. And so over this whole time period, which was 2003 through 2009, about 78 months, there was a depletion of about 20 cubic kilometers. Okay. Most of it occurred, which is 2/3 the volume of Lake Mead. Most of it, you know, was for irrigation, to grow food. And so most of it occurred here during the drought. And why did it occur? Because this is when the surface water allocations were cut way back, right? Like cut back by like 90% because there wasn't very much snow. And so we've got the whole delta smelt thing, and you know, we have to find this balance between the environment and the ecology and growing food and human needs. So we've done a similar study in India that was published a couple of years ago. Same thing, just a much stronger signal. It's a transboundary aquifer. I mean, you were going into Pakistan here, so this one had its share of implications, as will this one. This is the Middle East, and so you just repeated it. And again, it's about there's about 100 cubic kilometers of groundwater loss in the time period that we studied. So that's a lot of water, and one that will probably have implications in that part of the world. In fact, it's happening all over the world, and so these are the aquifers that are those red from the red spots in the map. So I just plotted out the time series. So, you know, some places are gaining water, some places are losing water. I just put, you know, I think these are critical because we already rely on groundwater there. Okay, so this points to the need for a sustainable water management in the arid and semi-arid regions. You know, like we didn't know, we knew that, but this just puts numbers on it and helps us to see, you know, how rapidly it's happening. I can tell that I'm running out of time, so let me just finish up with this slide. This slide. It's hand drawn. I love it. I think of it as charming. I've had students redraw it for me. I even had a student's wife redraw it for me. She hated it so much, but I like this one. I drew it, you know, one finger on the Mac. So what I'm trying to show, I'm trying to get at where I think we're going in the future, okay, with respect to variability and water cycle acceleration. And long story short, I think it's not good. So here's temperature versus time, okay? And if you think about glacial, interglacial periods, and I used to teach this let me elaborate on that. So of course temperature, historically through glacial, interglacial periods, goes up, right, in the middle of an interglacial period, and here we are now, and then it goes down. And so we can think about what the water cycle is doing in the corresponding time frame. And so when it's super cold, like say, if you go up to Greenland or Antarctica, all the water's frozen. So the water cycle is basically inactive, okay? And then as things heat up, like you come to the present, so I'm just trying to show a storage time series here. That's what this is a low amplitude storage time series for the ocean or for the land, okay? Well now, we're sort of where we are now, and so, there's water moving in the water cycle, right? And so there's ups and downs, and there's variability. And so, arguably, the water cycle's been accelerating for, 20,000 years, okay? And what I used to teach about global change in my introductory geoscience classes or earth system science classes was, well, we're really only worried about the short term because in the long term, the orbital forcing is going to take us back down here. It's going to be really cold. And so, maybe the water cycle would, slow down again if we're just focused on water. But we now know that we're not going to go back here, right, because the greenhouse forcing is greater than the orbital forcing. So temperature is not going to go down here. So temperature is going to go up. And if temperature goes up, then what's going to happen with the water cycle? And so I just drew this, this is all I can do. More variability. And so really, I guess, if we want to quantify it, we have to ask, so maybe in glacial times, the variability, the strength is way down here. This is my plot of water cycle strength. And maybe in the future, it's going to be way up here, okay? And so I think we need to start thinking about what the implications are of that. So, I have lots of doom and gloom stuff here, but I think this is a good place to stop. So happy to take any questions. So I haven't personally, and so that's a kind of study that you need multiple data sets because GRACE is only going to see a mass change, right? And so the permafrost would have to, the water would have to melt and then leave. So some people are doing it. Isabella Velaconia, who I work with at UCI, is working with some people at JPL. I haven't seen anything published, but it's not my area of expertise. I think it could be done with other data sets. Oh, yeah.
So we know that there are a lot of decadal scale or longer climatic oscillations. So
Yeah.
do you have real confidence that these decadal trends that you ascribe to
Yeah, right.
these phenomena are
Right.
ones that are cyclical?
Yes.
Especially the seismic ones?
Sure. Okay, so the question was, there are lots of oscillations that are longer than the time period of the GRACE data. And so what sort of confidence do you have in the trends? And the answer is we're confident in the ones where we were already confident. And that's the truth, because it's an excellent point, right? You need longer time series to really understand an emerging trend. A lot of what I showed today was really metrics and methods, right, which are independent. But the places that, a lot of the areas of groundwater depletion, I made the comment earlier, we already knew that was happening. So that's sort of in response to, that's how I answered that question. Where we knew it was happening, that's where we have the most confidence. It's just that now we can quantify it. So we really haven't found, except for maybe one area, any new areas of groundwater depletion or any new area where there's some unknown source of water. What we're able to do is quantify in a holistic way the change and the pattern. And from the pattern, you can really see that human fingerprint. But yeah, of course, we need more data before we have a lot of confidence in the trends.
So you've been talking about groundwater depletion. Do you find that the rates of groundwater depletion per person level or per area level of the different basins are about the same?
Yeah, I don't know. Yeah. That's a good question. And so we're doing some work. So our take on like the various stress indices is to try to use the GRACE data to try to incorporate that. And that's sort of work in progress, but that's a good question, and I don't know.
I think you made a comment that substance like that has no effect on the signal that you see. I always thought that gravity had to do with masses and 1 over r squared distance and that substance would affect that.
Yeah, so that's a good point. So I don't know, is the mass changed, right? I mean, we just have to look at the numbers, right, and see, what's gonna, right? It's the r squared versus the mass. Which one is bigger? Good question. Right. Yep.
Some of the early maps that maybe you didn't describe, you had the oceans included.
Yeah.
And there were some, let's say, signals.
Yes.
Do you have any interpretation of those?
I don't. No, I avoid the ocean like the plague. Except I have a whole group of colleagues that works on it and can see changes in currents and changes in bottom pressure. I don't try to go there. I'd be stretched too thin and would make embarrassing mistakes. So all I really do is look at the macro. And when it comes to the ocean, global ocean. I think the biggest thing is the config. It would be adding like another, and I don't really understand the details, but instead of it being a 2 satellite mission, a 3, different configuration. I don't think getting any closer would help, or changing the distance. A little bit of the accuracy with which the intersatellite distance. So that could be I don't know, laser or something. So a little bit of improvement there. But I think the big push to increase the resolution is to add in a bunch of pairs of GRACE satellites. Or people talk about a pendulum where you've got the 2. And then you've got one kind of zigzagging right now. Right? So last winter it went up a little bit, but certainly not all the way. And I haven't seen what's happened this year. So it went up a little bit, but not a huge recovery. So, and that's why I think there's a lot of information in these data that go underutilized. And also, as the faculty know well, we're not set up to continuously monitor. We don't go into operational mode. A lot of what we do is research. Our students write dissertations, they figure out some new way or some new science to do something, and then it kind of gets left behind. It would be wonderful to be able to continuously monitor groundwater all over the world and archive all these data sets, but we're not an operational, we don't do operations.